Welcome to classes on inorganic chemistry. Today's class is class number 22 and it is continuation of class number 22, continuation of class number 21. It is on DNA block element and today is the last part of a block element. So though a block element comprises of 14 elements and sometimes it is taken as 15 elements. So I am not following up on controversy. Let me assume that the block elements are 14 elements each. These elements are Lanthinoids and Actinoids. So why these elements are called as block element? In short, I am telling you that it is only because of the fact that last electrons progressively adds up in f orbital. That's why these elements are called f block elements. So often you will be disturbed with the electronic configuration of these things. Today I will show you the small trick how to write the electronic configuration, and you will not learn each and everything in details. I will show you the trick and from where the questions, the probability of asking questions even in entrance exam. Very often questions are asked from this part. Am I right? So first one is a lanthinoid. Elements starting, atomic number starting from lanthinoid, the elements atomic number 57, and from this the next element cerium starts from cerium, that is from 58, that is 58 to 71. So you should at least know the names of this element along with the atomic number. Then it will be very easy to write the electronic configuration, because each and every electronic configuration is a lot of use to explain a lot of factors and properties. So these elements are, in short, I am just telling you: cerium, praseodymium, neodymium, promethium, samarium, europium, gadolinium, terbium, dysprosium, holmium, iridium, thulium, ytterbium, lutetium. It is 71. So before writing the electronic configuration, remarkable and important elements. This is cerium, so I have answer called cerium. Let me first write one thing very important. You listen. The electron configuration starts from a lanthinoid, starts from xenon and 4, 5, 6 S, D, F, F 1 to 14, 0 to 2, 0 to 2. So here, this is general electron configuration of this. Xenon is 54. From 54, we starts in this way. The striking point here is D starts from 0 to 2, and it will not proceed further, and S always up to 2, and then F 1 to 40. Now let me write only one. First of all, cerium. It is how much? It is 58. Am I right? So this is xenon. It is 54. You write 4, 5, 6 S, D, F. So minutely follow. Here S is 2 and D is 1. That's why I have marked it by red. Ready? Am I right? So you see, always S is 2. Always S is 2. So 58 and 2, 60 and 61. Sorry, 58. It is 54, 56, 57 and 1 here, 50. You count these two fast, and what remaining you put on F. Next one, come to gadolinium. It is 64. It is very often asked in entrance exams, also in your class exam. Four, 5, again it is 2, it is 1, and it is 54, 56, 57 and 7. Now again come to lutetium, 71, xenon, 4, 5, 6, S, D, F. It is 71. You learn it by heart. 71. This is again 2 and this is again 1. 2 and 1, 3. 54, 3, 57. This is 14. So you count this one. So I have not written any other because of the fact that the exception is here is in each and every one D is 1. So these things, these 3 configurations are of utmost importance to learn. And when D is 1, it is exceptionally D is 1, S2, 1, S2, 1, S2. So you have got 3 and the left will be on F, 4F. So you write the configuration in this way. So what about the configurations of other elements? All other elements have configuration D0. Am I right? You've gone writing S2 D0, S2 D0, S2 D0, S2 D0, and what remains you put on F orbital. So you write only exceptions are cerium, gadolinium, and lutetium, where you will get D1, D1, and D1. And when you get D1, you will get F7, F14. It is stable. Here F1, it is other things. And what is the stability of this one? Either F is 0 or F is completely half filled, 7 block, 7 completely half filled, or F is 14. These 3 configurations are of very stable. So you learn about these things. Nerd, (92) 103 atomic number and starts from thorium, protactinium, europium, you are getting 4 where D1 configurations occur. One is protactinium, uranium, neptunium, plutonium, neptunium, and curium. So protactinium, uranium, neptunium, all are D1, and curium is D1 configuration. Other were exactly the same as earlier. S2 D0, S2 D0, S2 D0. Only keep which one has got D1 configuration. In the previous one, I told cerium, other called gadolinium, other called last one lutetium. Here I am telling except first one where F not F equal to 0, we are getting protactinium, uranium, neptunium, and cadmium for D1, and there is a bit peculiarity in lawrencium where P is 1 and where this will be 7P1. Now I am writing the general configurations of actinoids. This is the starts from radon. It is 86 and 5, 6, 7, S, D, F. As earlier it is like this. So this is simple configuration. So here again D is up to 0 to, not like earlier you write 1 to 10. You should not make this mistake. This is of this one. So now you minutely follow one of the very important thing. I will differentiate lanthanum and actinium, and this will be the half of your whole chapter. If you can minutely follow this chapter, you can answer a lots of questions from this one, and lots of questions are being asked from this. So in short, these are you please minutely follow these things, the distinctions. A lots of questions very often asked, what are the similarity, what are the differences, and lots of short questions are there from you. Please keep it in your mind. The general electron configuration I have shown is that is 86 and that is 54 xenon and radons, and you can write yourself. I have shown where there is some exceptions are there. Number 2 is less reactive and more reactive. I will come on this point a bit later on. That one, the common oxidation state of both the series lanthanoid actinoids are +3 and +3. All of this compound will, this series of the compound will show +3 and +3 configuration. But besides, there are other oxidation state is +2 and +4. This cerium will show +4 and europium will +2. You will find it in explaining the questions answer. I will explain this one. And besides common oxidation states, the lanthanoid actinoids will show 2, 3, 4, 5, 6, 7 oxidation state, and I will explain why it will happen. So next one. So basic difference you will learn first of all. Next, sorry. Magnetic and spectral property is shown by the lanthanoids, and the same similarities magnetic and spectral property are shown by the actinoids. Then oxides and hydroxides are less basics. I will explain on when I will explain the explanation of some questions answer. Again, oxides and hydroxides are more basics. And next one, less tendency to form complex. This is very important because the size of the lanthanides are comparatively a bit bigger than the size of the actinoids. And charge density, the complex formation depends upon charge density of charge on the cation. And this charge density is measured as the amount of charge above and the size below. If the size is bigger, then charge density will be smaller. Since the lanthanoid size is bigger, hence its charge density is small, and hence since its charge density is small, it has less tendency towards complex formation. But charge density on the other hand for actinoids are more, because the size of actinoids are smaller than lanthanoids, and the charge density equal to charge divided by size of the elements of the series, and these are smaller in size, so small part denominator is small, so answer is big, so charge density is bigger and higher, hence it has the higher tendency to form charge complex. And they do not form oxocations, but they form oxocations. And 4 orbitals are deeply buried, so when you will see the configuration, you will say it is deeply buried, and the 5f orbital is open to the environment, and that makes the study of actinoids. Yeah, you can write another thing. Study of lanthanoid is not difficult. DIFF. Study of actinoid is, or chemistry of actinoid is complex. So this is all about the differences and similarities between the lanthanoid and actinoids. So far I have got from the structure, I have given you in tabularized form so that you can't do not have to waste much time on thinking about the topic. So in a nutshell, I have given you the sum and substance of the topic in a tabular form, upon which a lots of question and lots of explanation you will find these terms over and over again. So before getting these terms in the questions answered, you should know the proper meaning of this term. The term you have got already in the first year, but I don't know, do we have this concept upon these terms, shielding effect. Very often this term is often used in answering a lots of questions answer, and lots of chemical and physical properties is resting upon this factor. So answer very in short way, in very concise manner, the answer or definition of this one is the attraction between the outer electrons and the nucleus decreases as the number of electrons between them and the nucleus increases, is called shielding effect. What does mean shielding? Shielding means screening. What does screening means? Means barring up. What does screening means? There is intervention. What does protection means? Shielding means protection. Shielding means screening. Shielding means disturbance. Shielding means warning. That is, in the nucleus there are proton and neutron. Proton is positively charged, and lots of shells are there. In the outer shells there are electrons. So the question is that proton should attack the outermost electrons. So what's happened? As soon as the number of electron enters in the inner shells, the attraction between the proton of the nucleus to the outermost shell's electron decreases, and this decrease is due to screening of this electron, which prevents in attracting proton upon electron towards itself, and that effect is called shielding effect. Now what does shielding effect is applicable? The s orbital is spherical, you know the shape. S orbital is the highest shielding effect, as if the electrons are on s orbital, it will shield or it will prevent of attracting power of the nucleus towards the last electron will be influenced at a large extent. So s orbital, then p orbital, then d, then f. F is the least shielding effect and s is the highest shielding effect, highest shielding effect, screening effect, highest preventing effect, highest warning effect that will wall between the attraction of the nucleus upon the electron on the last shell. So that is shielding effect, and I will explain how this will come in explaining the question's answer. First of all, you should know the concept upon shielding effect. Again, another very important term is very important terms and very often asked in entrance exam to find out the effective nuclear charge, and also in explanation and lots of questions answer you will find this term ZEF, effective nuclear charge. Now why the term has arisen to explain, it is needed to explain effective nuclear charge. Nuclear charge itself is the nuclear. Now what is effective nuclear charge? You see chlorine, these are 17 proton and it has 17 proton and 17 electrons. 17 protons are attracting 17 electron, but at the last shell, if you draw the configuration to 8-7, last electron shell configuration is 7 electron. Now question is that a 17 number of proton will attract the last 7 electron in the as it is attracting upon other shell's electron. Naturally not. There is some decrease in the effective nuclear charge. Effective nuclear charge is not always the same as the nuclear charge itself. That is Z. Z is not always equal. And sometimes it is equal in case of 1s2. If there is no other shells, it will be equal. Effective nuclear charge is not. Effective means what the definition? The net nuclear charge pulling to the outer electron towards the nucleus is called effective nuclear charge. Net, what does net means? Net means not actual. Gross means everything. Gross salary means DA, medical allowance, each and everything. If you sum up each and increment, if you sum up each and everything, it will go gross. And if you subtract the tax, the GIS, GPF contribution like this, if you subtract all this and whatever amount you get after subtracting from the gross amount, that is called net. So when the word net enters, means the total is 17, but that 17 is not exactly attracting the outermost electrons towards itself. Means there will be some deficiency in electron number that will not reduce, but there will be some intervening effect. There will be some intervening effect. So what is this effect? I will explain. I will explain it later on. Means it is found that approximately all 17 electrons are not attracting the last electron. Approximately about 10 protons are attracting the last electron. Now this what about this last more 7 electron? That says there is two forces. One, it is trying to attacking the outer one, and there is some intervention due to the population of electron in various shells, and these two end. One is screening, another is attacking. The two opposing force cancels the nuclear force, and it reduces to net level of 10, and that 10 net level is called effective nuclear charge. And this effective nuclear charge, a very decisive factor to explain ionization energy. In your chapter I will explain what's happened. So as you move from left to right in the period, sodium, potassium, sodium, aluminum, silicon, phosphorus, sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, argon, potassium, calcium, scandium, like this, if triple block up to argon, if you go on, you will find in the first year you have seen, as you move from left to right in the periodic table, the size decreases as the nuclear charge increases. Up to this you have stopped. But now we will include a term that on moving from left to right, no doubt the size increases, and this increase in size is due to the fact of the ZEF, effective nuclear charge, is going to be increases. And the more the effective nuclear charge, more will be the production, attraction of the last electron towards itself, and lesser will be the size. If the nuclear charge 6, 7, 8, 9, 10, if increases by 1 and 1, so more is the positive charge in the nucleus, the shell remains same in the period, same shell electrons are coming, incorporating, entering. So shell remaining same, distance remaining same, but if you find out the effective nuclear charge and if you see the effective nuclear charge increase 1 by 1 by 1, that is, you are getting plus charge is successively increasing. So at a fixed distance, the electron will be attracted, outer electron will be attracted more and more in strength, and the size will be decreased. So in other term, we will explain the size will decrease as you move from left to right in the periodic table, as the effective nuclear charge increases from left to right. So if the size decreases means effective nuclear charge increases. So along with the size, effective nuclear charge, the relation is the size will increase if effective nuclear charge increases. Size will decrease if effective nuclear charge increases. Now what I told is effective nuclear charge. How we will calculate what is the total amount of effective nuclear charge in an element. So let me take in one example. In chlorine, it is 17. You can write effective nuclear charge. The formula is Z minus for this effective nuclear Z minus S. S is the shielding electron. S is the shielding electron. So how will you find out shielding electron? Shielding electron means the electron which is involved in shielding or screening. As earlier I have explained the term, shielding electron is equal to atomic number minus valence electron. Now what is the atomic number? Atomic number is equal to 17, and what is the valence electron? 287. The valence electron is equal to 7, so it is 10. So you have got S is equal to 10. Now come to that one, ZEF is equal to Z minus its atomic number. S is the shielding electrons. Number of shielding electron is 10. Here it is atomic number is 7 minus 10 is equal to 7. This is one type of calculation of atomic effective nuclear charge. Z minus S, where S is the shielding electron. Shielding electron is the atomic number minus valence electron. Atomic number minus 10. So atomic number minus 10 is equal to 7. So you will get a bit different value when we measure this by Slater rule. Slater is a famous rule and it is very relevant rule. And when you talk about this one in higher entrance exams, a lot of when you will be asked to find out the effective screening constant or Z effective in case of hafnium, or in case of tantalum, or in case of europium, or gadolinium 64 atomic number is a lots. So it will be a tough case for you to find out with the help of this rule. So you can use the Slater. What is Slater? According to Slater, Z effective is equal to Z minus sigma, where sigma is the screening constant. Screening constant. So in this case, it is a very important thing. You please write to know if you are not willing, you can skip for entrance. It is very important. I think it should be known to you. So one is it is for electronic configuration of chlorine. Am I right? So 1s to 2s to 2p6 and 3s to 3p5. If you want to find out the sigma screening constant for p electron, first of all you should do one thing: 1s, twice s, twice p, thrice s, thrice p. You first make it block like this. Mind that D and F should be single. You should not combine with other. S, SP, SP, D, again S, SP, D, F alone, D alone, and other things you block in this way. Am I right? So what's happened? If you are asked to find out the sigma screening constant for this, and you are asked Z effect for this p electron. So what's here is 2, 2, 6, 2, 5. So the rule is that if if this block is assumed to be n, this is n minus 1, this is n minus 2. So for n, if it is S and P, the value of this P or S is 0.35, and value for next n minus 1, if it is n3, this is 2, n minus 1, this is n minus 2, 1, am I right? So this will be, for this group it will be 8.5, and for this it will be 1. You should know these things only. If first one is n, second one is n minus 1, last one is n minus 2, and first contribution is 0.35, and second block contribution is 0.8, and third one is 0.1. So now we see the beauty how to calculate. So first come to this one, minutely follow. If it is given P, so you just reduce one electron. There is 5 to 7, you make it 6. 6 into 0.35, am I right? Plus, you add up, you multiply. Then 6 to 8, 8 into 8.5, you will get another result. Next 2 into 1. You find out the result. You yourself find out. For time sake, I am not finding out this thing, and what I know that total value will be your sigma. That total value will be your sigma, and you put this sigma value here. That sigma value, say it is x. You put this sigma value here, 17 minus x. What is x? I don't know. I have not calculated. I think it will be 6 point something. So there will be a big difference from earlier one, that is 7. I think it will be 6.1, and it is most reliable rule, is Slater rule, very famous rule. So these are the two things, important things. I have forgotten to tell you that if it is given 74, if it is 103, if it is 71, lutetium, lawrencium 103, if the higher molecular atomic numbers are given, so with the help of Slater rule, it will be difficult for you to find out the electron configuration. 1s, 2s, 3s, 4s, 5s. After this, we learn very easily. But for higher entrance exam, you should know how to write, because you can make block, and then you should calculate. Am I right? So to do this, one technique is see. Minutely follow, very important thing. Just you draw in this way a figure, and you with a gap you give 1, 2, 3, 4, 5, 6, 7, 8 in this way you write, and you give arrow this way, arrow in this way, up down in this way. It will go in this way. Am I right? So you put 1s, 2s, 3s, 4s, 5s, 6s, 7s, 8s, all below line are 8s. And mind that from these two you don't put anything above, because 1s, 2s earlier, if you write the earlier number of 2, it will be 1, but in the above principle you will never get 1 twice. So it is not repeated. So you don't give above number. Above of below, before of 2 is 1, so 1 is repeated. So you give up these 2, and from here you start 3. You go 1 up. The previous of 3 is 2. The previous of 4 is 3. So I have gone up to 2. 1, 2, 1, 2. Now come to this one. You go 3 number. 5, 4, 3, 6, 5, 4. 2 number. Then you go 4 number. 654 765. So now you see the beauty of writing. This is S, SP, 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 D, SP, D, SP, DF, SP, DF. You can, I hope you can write 100, 0, 18 up to 1s, twice twice p, thrice thrice p, 4s, thrice d, 4p, 5s, 4d, 5p, 6s, 4f, 5d, 6p, 7s, 5 f, 6d, 7p, 8s, and you put on right and block. You can find out whatever number at 8164 gadolinium and whatever is given you can find out. Am I right? So in short, this is the way to write the whole configuration it is required. But for your exam or class exam point of view, you can write by xenon or by radon in a short way. No need to show and kill times. For letter rule, to find out the screening percentage sigma, or to find out the ZEFF effective. So you need to write all this configuration in open way. So you should use this. Very important. So you see, very important one, very important for exam point of view. Also, Lanthinoid context on the definition along with this, and lots of properties depends upon this one will be asked, and I will explain one by one gradually. So you see, first the steady decrease of atomic and ionic radii in the Lanthinoid series decreases in the the steady decrease of atomic and ionic radii of Lanthinoid series decreases as we move. As we move from left to right is called Lanthinoid contraction, and this is due to the poor shielding or incomplete shielding of the f orbital. A bit earlier I had told you the shielding effect, that is screening effect. If it screens the nucleus against the attraction towards the outermost electron, so outermost electron will be loosely bounded. And if it cannot screen, that is, if does not give an interference, doesn't cause any screening effect, does not contribute to the screening effect, then the nuclear proton will very easily attract the outermost shell, and thereby the size will decrease. So we have seen S has greater screening effect than P, then D, and then F. F is least screening effect. So we are dealing about the f orbital, f block elements where the last electrons are progressively entering and filling the f orbital. That's why they are f block elements. Am I right? So if the F is entering F, D, S, last one is S, then D, then F. So progressively F orbital is or subshell is being filled up. Am I right? If this filled up F orbital doesn't have the proper screening effect, it cannot screen the increased nuclear. So what will happen? Consequently, the more and more nuclear positive charge will attack the outer electron with greater strength, and thereby size will decrease. Means effective nuclear charge will increase. Am I right? As we move from left to right in the periodic table due to poor shielding of f orbital, and that is why the size from left to right in the Lanthinoid series from 58 to 71 successively goes on decreasing due to poor shielding of f orbital or increase in ZEF or effective nuclear charge, and that phenomenon or the reason is called Lanthinoid contraction. Lanthinoid contraction. Now I am going to explain explanation or uses of Lanthinoid contraction as a whole. In whole chapter, these are things are given and very often asked in entrance exam, also in your class exam. One is say zirconium and other is hafnium. The atomic number is 40 and one is below other. Zirconium, Zr, and hafnium is below this. This is 40 and this is 72. I think this is 40 and this is 50. Am I right? So what's happened? When you move from top to bottom, the new shell centers, and when new shell centers, the nuclear distance from the outer electron increases, so nuclear force decreases, size expands, size increases. But what's happened? As you move from in this way 4D series, and consequently we come to 5D series, and if corresponding element, zirconium and hafnium, one above the other, as per rule, zirconium should have lesser size than hafnium. Hafnium should be bigger than zirconium. But in fact, we have seen the size of these two are same. Why? Because when we move from this to this, so whenever we will come to this series of 5D corresponding to zirconium, that is just below this one, the one shell increases and this is 4F. Am I right? So the shielding effect of 4F is very poor. So it cannot screen the increased nuclear charge towards the attractive force of the higher electrons. Thereby, as this has poor shielding effect, so it is no longer intervening the increased nuclear charge to attack the outermost electron. Thereby, it will attract the outermost electron in a greater strength, in a greater force. Thereby, size will not increase, size will decrease. Thereby, these two will remain same. So it is 159 picometer and it is 160 picometer. So more or less these two sizes are equal. So how will you explain? You will explain that from zirconium it is in 4D. It is corresponding of 5D element is 4F. It is 40 and 72 is electronic configuration due to introductions of new F shells, and this F shell has poor shielding effect and it doesn't intervene the increase the attractive force of the proton in the nucleus towards the outermost electron. Thereby, its attractive force increases and size decreases. That's why these two size more or less equal. So, lanthanide contraction has an application that we can explain the size of these two. Why it is not bigger than this? Why these are the same? We can use the term contraction or shielding effect. Concept of shielding effect I have earlier used. We can use the shielding effect. First one. Second one is 5D. This series has similar chemical and physical behavior. This question is asked very often. You can also explain it from yourself now. Why? Because 4D and 5D, I have seen you that introductions of a new shell in the 5D. So we have got 4F orbital, and F orbital has the lower shielding effect and it can't shield the increased nuclear charge, thereby the attraction increases, thereby size decreases. Due to this, so 4F series, 4D series and 5D series, 4D series, 5D series element should have bigger size. But due to this fact, I have already explained, these two series have similarity in the size, almost same. As these two series, as the element of these two series has similar size, more or less almost the same size, they have got similar chemical behavior and physical behavior. Second part on lanthanide contraction. Next one is basic character. Basic character. We know basic character decreases from lanthanide, means cerium to lutetium. If you assume this hydroxide, cerium hydroxide, and to this, you will see the basicity will decrease and acidity will increase. Why? Because as we move from left to right in the lanthanide series, the size decreases with the bigger size. It is basic in nature. When size decreases, it becomes acidic in nature. Due to smaller and smaller size towards the right, the hydroxide basicity will decrease. At the left, acidity will increase. Again, this is due to lanthanide contraction. We can use explain another question: why basicity from lanthanum to lutetium decreases as you move left to right? Because of the decrease in size or increase of effective nuclear charge, or due to lanthanide contraction disorders. Amount of, again, what is ionization energy? Ionization energy means the amount of energy required to release the last lowly bounded electron to make it cation is called ionization energy. As you move from left to right in the lanthanide series, we see the size increases along with the increase of the effective nuclear charge, or the due to lanthanide contraction size decreases, or the poor shielding effect of fluorine orbital size decreases. So what happens if the size decreases, the attraction between the nuclear force and the last electron will increase, and it will obvious that the amount of energy to release the last electron from left to right. As we move from left to right, will become tougher and tougher, will become higher and higher amount of energy will be required. As the higher and higher energy amount of energy is to be required, we see that at the earlier part of the lanthanide series, the ions are formed, but as we move from left to right, we see that ions are not easily formed, and because of the fact that they are not readily formed ions, and if these ions are formed, it becomes very unstable. So questions ask why the ions formed in the lanthanide series are unstable. This is because of the fact that the ionization energy of lanthanides or actinide series are more. That's why it is required more energy to release the last electron. Hence, if ion forms, it becomes unstable. Oxidation state for the lanthanide and actinide. If you explain a lanthanide and actinide, very often asked the question, explain the oxidation states of lanthanide and actinide. Very easily, very beginning I told you that both lanthanide and actinide have common oxidation state +3, and for lanthanide we get 2 more plus oxidation state is +2 and +4, and for actinide besides 3 we get 2, 3, 4, 5, 6, 7, all are plus. Am I right? All are plus. So part 7, oxidation state +3 for lanthanide series, and other 2 oxidation state is 2 and 4, and in case of the actinides we get 3 and +2 and 4, 5, 6, 7 besides +3. Now my question is that a question always asked in the entrance exam, why there is more oxidation state in case of actinide than lanthanide. Lanthanide have limited 3, and we have seen in actinide lots of oxidation states are found in actinide. What is the reason? Number 1, the reason is that in actinide we get this radon and this. Am I right? The electron configuration is this 2, 1 to 0, 2 and 1 to 40. You know it. So we see we have got 5f, 6d and 7f, and these 3 energy levels are comparable energy. Comparable energy level. They have a very least difference in the energy. That's why they are called comparable energy levels. And due to the presence of 5f, 6f, and 7f comparable energy, they very easily take part in making bond with the other one, making reactions or doing reactions with other one. So due to the participations of all these shells, and due to comparable energy levels, their oxidation states are high. Am I right? Next part is chemistry of actinides complex. Why? Number 1, the 5f orbital is exposed to environment, but 4f orbital is deeply buried. Here it is open to the environment, so more possibility of oxidation reactions and other type of physical behavior. Hence, the chemistry of actinide is complex. Number 2, these 3 levels of energy are having comparable energy levels, so they take part in bonding and they have a lots of oxidation states, and due to this, the chemistry of actinide is complex. What is number 3? Almost all the elements of actinides are radioactive, and the elements are radioactive is their chemistry is tough. Due to these facts, the chemistry of actinide is very complex. One is 5d orbital is exposed to environment. Then was 5f, 6d and 7s are comparable energy, and all they have lots of variable oxidation states, and almost all the elements of actinides are radioactive, and hence their chemistry is complex. Another question, 4d, there is similar chemical behavior is seen in between 4D and 5D. Explain why. Answer: because of the fact that when you move from 4D to 5D and 4F shell appears, and this has a poor shielding effect. Due to poor shielding effects, the attraction force of the nucleus to the outermost electron becomes small. Hence, the size decreases, and almost 4D and 5D have similar size, and due to this, there is similarity in chemical behavior also. Next point is on paramagnetic and color. Because maximum of they are paramagnetic and they show color due to FF transition, and this they are paramagnetic due to unpaired electron, due to presence of unpaired electron. But mind that there is a question. It is a bit tough, but I will just explain a bit. That is mu. If you want to find out the paramagnetic mu for any substance, sometimes you are asked cerium. You do the configuration of cerium 58. You go on writing 58 and you use last 2 and 1. You will get F1. I think yes. This will be 4F1 if you draw. So you put here. Actually, in earlier case we wrote n into n plus 2 Bohr magnesium. N into n plus 2 Bohr magnesium. You can BM. You can write this one, but here in this case there is orbital contribution along with the spin orbital momentum. Spin orbital momentum, it is a bit bigger class and a higher class. There is spin orbital moment, angular moment, and orbital concept is there. This is the basic difference between transition element and block elements. Where in transition element we never get orbital concept, orbital contribution here, and here there is spin angular momentum. So also orbital. This is L is equal to number of unpaired electron. Orbital configuration you have to calculate. So in case of transition lanthanide actinide, we see in case of paramagnetic behavior there is orbital contribution besides angular spin angular moment. Cerium 4 is oxidizing mind that once again you are asked the question, cerium is oxidizing and the europium 2 and Y/2 plus is reducing agent. Reducing agent means loss of electron is called reducing agent. The substance which lost electron and get oxidized are called reducing agent. Am I right? So yes, we have seen in lanthanides, so the stable electron configuration or common electron configuration is +3, is very stable. Am I right? So if you want to get +3, you should lose one electron. To lose electron is means reducing. So uranium 3 plus, you please draw the configuration. Am I right? You draw the configuration, you will find. But I am just telling you that uranium 2 positive, it will lose one electron more to get UN, because this is the stable electron configuration. It is xenon. So this is 54. Am I right? This is 54, and you write 2 here. And I have shown you earlier that there is no exception in D. All D should be 0 except cerium, gadolinium and lutetium. So you put this here 0. So total you are getting 2. So 54 and 2, 56. We need how much? 63. 63, 56. It is 7. Am I right? So when you lose this one, you are getting uranium 2. So again, if you lose 1, you will get uranium 3, because E3 is stable electron configuration. So UB2, again you do in this way. Whereas here cerium oxidizing means it will gain electron. On gaining one electron, again it will get, you will get C3. But cerium, and the electron configuration of cerium is xenon 4, 5, 6 SD F, and it is exceptional. I told you that should be 2 and that should be 1. It is fixed. 3 elements. Am I right? And lanthanum also, it is 57. It is also controversial. exceptional. Here also D1, mind it, but there is no F. Lanthanum is also like this, mind it, D1, no F. So D2 then 3, it is 54, am I right? So out of 54 and 3, 57, and how much we need? We need 51, 58, we need 58, so we need here 1. So the configuration is, you make it fixed because it is exceptional. You have told you earlier, then 2 and 1. So 54, 56 and 57 and 158. So it is 58. Am I right? So when you we can lose all 2 and 1, 3 and 4. It is C4. Am I right? C4 oxidation state. So out of C4 oxidation state, there is nothing. When you will gain 1 electron, it will be 4F1. Am I right? So it can gain electron to get C3. So it is oxidized. Like lanthanide contraction, we have seen in lanthanide there is 4F, but we have seen in actinide there is 5F. So 5F is more having more weak or poor shielding effect than 4F. Due to this fact, when you move from left to right in the actinide, we will find more and more attraction force because the 5F is furthermore weak in shielding effect. So nuclear charge will attack the last electron even more stronger than the lanthanide case. So the size of the element in lanthanide element of actinide is smaller than the lanthanide due to furthermore poor shielding effect of the 5F orbital in actinide. So there is also decrease in size from left to right due to the presence of furthermore poor shielding effect of 4F, and size will decrease from left to right along with the increase of effective nuclear charge. Hence, and this decrease in size, further decrease in size in lanthanide is called lanthanide contraction due to poor shielding effect of 5F, poor shielding effect of 4F lanthanide, poor shielding effect of 5F actinide. So another question, cerium shows Class 2 oxidation state. I have already shown you. This is I have already shown you. This is 2 and this is 1. Am I right? So atomic number is equal to 54. Genome is 54 and 54 and 3, 57 and 1. This can very easily lose this 2 electron to make cerium 2 positive to give electron configuration of this. So it can lose 2 electron. So it will show YB will show this ytterbium, and the atomic number is, I think it is 17, and this is 54, 5, 4, 5, 6, X, D and F. It is 2, and there is no exception, so it will be 0. So you are getting 2, 54 and 56, 70 and 56, there is 4. So it will very easily lose these 2 electrons to gain stable electronic configuration, completely field electronic configuration of Xc 14. It is highly stable. Why? Because it is this. Am I right? 4, 5, 6, X, D, F. Again, it is exceptional. Am I right? I told you very earlier. And this is 54. Am I right? 54 and 3, 57. 57. We need 64. The atomic configuration, atomic number is 64. I think it is 7. It is completely half filled. So it will show Class 2 oxidation state on releasing these 2 electrons because completely half filled F orbital is found. Very often lanthanum 2 plus show no color, because if you go on writing, generally I will not write it, you yourself can do it, you will find no electron on F. So there is no effect transition, so it will not show any color, and it will also will not be paramagnetic because there will be no lone pair. Lutetium 3 plus is colorless, so also not attracted by the magnet. I think it is 71, and you write this 54, 45, 456, SD and F, and lutetium again it is exceptional, so it is 2 and this is 1, so you have got 54 and 57. I think it is 14. So lutetium 3 plus means if you lose these 3 electron, are you not getting stable electron configuration, completely field configuration? That's why lutetium ES3 will show +3 oxidation state. One question answer, another you will not show any color because d orbital is completely filled. Again, it is not paramagnetic because there is no unpaired electron in the f block element. Another point is given in your book. It is mismetal. Mismetal is a type of alloy which comprises of approximately 95% of lanthanum metal and approximately 5% of iron and traces of little sulfur, carbon, calcium, and aluminum. And hope you have enjoyed the class with utmost interest. I am soon coming with another interesting topic in the next time. Thanks a lot for watching the class.